Hello and welcome back to Discrete Mathematics. This week we're going to be talking about sets. So, what's a set? Often we need to group things together. And so we want to talk about what makes something a part of a group or not part of a group. Do different groups have elements in common? Are there elements, are there groups that are completely disjoint? They have no elements in common. There's a lot of different sort of things we can talk about with sort of grouping things together. And so we want to have a way of expressing that sort of using mathematical notation. And so the easiest way to think of a set is just, it is a group of, objects that contain, some objects are in the group and some objects are not in the group. And so we can represent that by a circle, call it S, that's as our set. And then we have an element X and we just draw that in the circle. If we draw it out of the circle, then it would not be a part of the set. Sort of a way of representing it. In mathematical notation, we write it as X as an element of S, using this little sort of weird kind of rounded E symbol. And obviously, if you have a slash through it, that means that the element is not, or the item X is not an element of S. And you can also say different things. I always say an element of, but you can always say X is in S, X is a member of S, X has the properties as though to qualify it to be a part of S, whatever you want to say. But X is a member of S, or X is an element of S, right? When you're trying to define what a set is, probably the most brute force way to do it is just to list everything in the set. Now, you can do this for really small sets. In fact, it's probably the easiest way of doing it for some really small sets, depending on what it is. So here we can just say S is equal to, and then, put out some curly braces and start listing all your elements separated by commas. Like I said, it works for really small sets. If I were to say the set of all the main characters from the sitcom Friends are Monica, Rachel, Phoebe, Ross, Joey, Chandler. Hi, why am I choosing stuff from the 1990s? I barely remember. But they are the main character. They are the friends in Friends, right? That set is fairly easy to write. Other sets will not be because they are huge. In that case, we're going to want something a little bit different. We may want to describe a set as a bunch of objects that contain a particular property. So here, we kind of do what we call set builder notation. Set builder notation is just X is an element of S, and X has a property P. The reason we sort of say that X is an element of S is often we're defining something for all integers. But this wouldn't necessarily include things that aren't integers, right? Things that have fractions as a part of them or something. Like, we don't want to consider that. We just want to consider the integers, and then we can define what like odd and even are, right? I can't define odd and even for something that isn't an integer. Right? We just don't have a definition for that. So anyway, we can sort of define kind of in general what bigger set it belongs to, as well as any of the properties. So here's an example. We're going to use set builder notation to define a set. So here we've got a set A, kind of our bigger set that we're taking out of, 1, 2, 3, 4, 5, 6, 7, 8. And then we say that something is in set B if X is an element of A and X is odd. So the elements in B would be 1, 3, 5, and 7. That works out just fine, so long as, in fact, you could probably actually, in fewer characters, actually just put 1, 3, 5, 7 inside of those parentheses. It would actually be easier to define it using the brute force method. But what if it wasn't A? What if X was just an element of the integers? Okay, well, now our set is actually infinitely big. There's no way I can write that using the sort of brute force method. I have to actually define it using set builder notation. Here's another example. So if we say that P are the set of all polygons, so P has all triangles, squares, pentagons, hexagons, septagons, octagons, novagons, decagons. I'm not going to try to guess what the 11 one is, but I'm pretty sure I'm wrong on the last two. Regardless, all the different possible polygons. We could say that H, which is the set of all hexagons, could be defined as H, the set H, is equal to X is an element of P, and X has 6 sides. If you have 6 sides and you're a polygon, then you are a hexagon, right? It's just another way of defining a set. There are some commonly used sets that sort of have universal meaning, and you would never want to name a set using one of these letters. But Z is the set of all integers. I know what you're thinking. Why do we use Z? It comes from Zalm. It comes from a German word that means number, right? So Z is the set of all integers. N is the set of all positive integers. We often call those natural numbers, which is why the N. And by the way, interesting, zero is not a natural number. The natural numbers start with 1, not 0. I don't know why 0 is not considered natural. I'm sure there's a very good mathematical reason for it. I just don't know it. Or it's tradition, one of the two. Obviously, Europe didn't have 0 until it got imported from the Middle East. So anyway, you can't write 0 in Roman numerals. R is the set of all real numbers. So all real numbers are numbers that don't involve that weird little I thing that represents, negative square root of 1, a number that can't exist, or square root of negative 1. There we go. But if it doesn't involve the little I, it's a real number. And then Q is the set of all rational numbers. Basically, Q stands for quotient, kind of related to rational numbers. But anyway, the only weird one is Z, and it comes from German. So, subsets. A subset is a set that is sort of smaller and contained within another set. It is a subset of a larger set. And so that implies that if you're a member of the subset, you're also a member of the larger set. So let's see here. We could say that, integers are contained within the set of real numbers, right? All integers are real numbers. Right? None of them have that little weird I thing. And so we can translate this to logic, right? For all x is an element of A implies that x is an element of B. That would mean that A is a subset of B. And we can express that with that kind of weird C with a line under it. And again, if A is not a subset of C, we just have a slash through that symbol. And so that's what we say. A is a subset of B implies that if x is an element of A, that implies x is an element of B. We can draw it sort of in a Venn diagram this way. B is the larger circle, A is the circle that's completely contained within B. Notice that if there's any overlap, if A kind of goes outside of B, then A is not a subset of B. A has some common elements with B, but it is not a subset. To be a subset, it has to be completely contained by the larger set. I say larger. Technically, they could be even, but we'll talk about that in a second. So we said that integers are a subset of the real numbers, but in fact, that relationship kind of goes on, right? Natural numbers are a subset of the integers. Integers are a subset of the quotients, the rational numbers, and the rational numbers are a subset of the real numbers. If we go back to our polygon-hexagon example, we can say that all, the set H, all hexagons, are a subset of P, all polygons, right? Because to be in H, you have to be a polygon. That makes sense. But we can't say that P is a subset of H, because it's not true. There's lots of polygons that aren't hexagons. And that's the case for most subsets, right? Just because you're a subset in one direction doesn't mean it goes in the other direction. What is it? All cognacs are brandy, but not all brandies are cognacs, right? Cognac is just a brandy that was made in the Cognac region of France. That's a weird example. Why would I go to cognac? Kid-friendly example. All thumbs are fingers, but not all fingers are thumbs, right? Thumbs are a subset of the finger set. To be a thumb, you have to be a finger. But just because you're a finger doesn't mean you're a thumb, right? It's a subset. And if you think about it, the only way you could ever have a set that was a subset of another set, that set itself was also a subset of your set, would be if the two sets are exactly identical, which is why I always say larger set, but technically they could be equal sets, right? You could have the exact same number of elements, and that would still be true, right? You are a subset of yourself, technically. But that's the edge case. Any other overlap, and you're no longer a subset. Speaking of which, so the empty set. The empty set is a set that contains no elements. Because it contains no elements, it is a subset of all sets. Every set has the empty set as a subset. In other words, if I take, all the students at Fresno City College, and that's my set, I could say, well, then how many of those students, I don't know, think 2020 has been a great year overall. That would probably be the empty set, right? Like the empty set is always a possibility, right? I could just have none of this set. Well, that set would be the subset. I'm lying. There's probably at least a couple of people that are having a great year. But regardless, theoretically, it's possible. And so what we say is for all x is an element of the empty set implies that x is an element of x, right? Like you can say that it's a subset for anything. And so you'll notice that we've already started using some logical ideas to describe sets. Because of subsets, we can talk about implication. And so there are other sort of arrangements or ideas when it comes to sets and how sets can be related that correspond to our other connectives, right? Your ors, your ands, your nots, your if and only ifs. And so we can talk about those a bit. The first is the union. So when you have two sets, the union of two sets is essentially saying that for any x can be either an element of A or it could be an element of B, right? So unions really kind of represent the or connective because A could be A or B. So if we were to write this in sort of an equivalence rule, right, we could say that for all x is an element of the union of A and B if and only if x is an element of A or x is an element of B. But notice that implication goes both ways, right? So when I say that, basically I'm saying that these two statements are they are equivalent. So when you're doing a proof, if you have x is an element of the union of A and B, you can immediately switch that to x is an element of A or x is an element of B by the definition of union, right? Which can be helpful because when you're doing proofs, you're trying to get from one statement to the next. If you're wanting to draw this picture, the union of two sets basically represents everything in those sets. So if, let's say, set A is fans of Green Day and set B are fans of Taylor Swift, then I am in the union of the sets A and B, right? What's that tell you? Well, not a whole lot. It means that I could either be a fan of Green Day and not like Taylor Swift. I could like Taylor Swift and not be a fan of Green Day. Or I could be a fan of both, right? You just know that I'm somewhere in there. I'm at least a fan of one of them. The intersection, right, A intersect B, is the set containing all elements that A and B have in common, right? This is the overlap in the Venn diagram. And so to say that something is in the intersection of A and B, you could say that that element X is an element of A and it's an element of B. So intersection really represents the and relationship because you have to be in both. So we can write that as a logical equivalence again, meaning that in proofs you can translate these two statements one for the other. It's if and only if. The implication goes both ways. X is an element of the intersection of A and B, if and only if X is an element of A and X is an element of B. Two statements are logically equivalent. And of course, like I said, in the Venn diagram, it's the intersection between the two. So if we have A represents people who are fans of Green Day and B are fans of Taylor Swift, I happen to be in the intersection of those two groups, those two sets. What can I say? I mean, Dookie, American Idiot, these are classics, love punk rock, and, Folklore. It was the album we all needed this year, right? Anyway, universal set. So, basically, the universal set represents kind of what we're talking about. It's our universe of discourse, our domain. It's only really needed because we need it to know the next concept, which is a complement, right? But what is it we're talking about? When we're talking about numbers, are we talking about integers? Are we talking about all real numbers? Are we talking about people? Are we talking about all matter in the universe, right? And so, we need to understand this before we can understand the complement of a set. So what's the complement of a set? The complement of a set is basically a complement it's an element of the universe of discourse, right? It's an element of the domain, but it is not an element of A, right? This is the equivalent of the not connected. It just means it's not in A, but it's still within whatever we're talking about. If I talk about, faculty members, faculty members, right? A is the set of faculty members. Then you are probably, I assume, unless you happen to be a faculty member who happens to be watching this video for some reason, in the complement of A, right? You are not a faculty member here at Fresno City College, but is this skull in the set A? By the way, it happens to be Halloween when I'm recording this, or near Halloween, right? Like, is it? Well, maybe. It depends. What's my universe of discourse? If it's all matter in the universe, then yes, this is also in the complement of A. This is also not a faculty member. But that doesn't make a whole lot of sense, right? So we'd probably say, well, no, we're talking about people. Okay, well, if it's people, then no, that's not in the complement because it's not what we're talking about right now, right? 2020, you always want to make a political statement, but I'm not going to this time. Anyway, point being, those are just not the lives we're talking about. All right, so equality. We can say that two sets are equal if being for all x, if x is an element of A, if and only if x is an element of B, right? Notice that's if and only if. It's bidirectional, the implication. So if x is an element of B, that also implies that x is an element of A. And so how do you do this, right? In order to prove this, the implication, again, goes in both directions. So you kind of have two proofs you have to do. You'd have to prove that given x is an element of A, that x is also an element of B. But then you have to go back but all that does is prove that A is a subset of B, right? Because we know that relationship. If x is an element of A implies x is an element of B, that's a subset. But if we can also prove that x is an element of B implies that x is an element of A, then we can show that the two sets are equal. Which basically goes back to our original idea, right? That two sets are equal if and only if, this one is a subset of this one and this one is a subset of this one. Then you know they must have the same size and have the exact same elements. They are the same set. And so we'll kind of run through a quick proof of this. So we've got three different sets here. X. All these are going to be elements of integers, right? So it's n such that 2k for some odd integer k, right? So basically, we know that n is even because anything in the form 2k is going to be even, but it has to be even where when you divide by 2, you get an odd number, right? So x is that set. F is the set where n equals 4k for some integer k. Now you probably notice that 4, why are we choosing 4? Well, it's because you can kind of pull a 2 out of it, and we'll see why that's... If you're intuitively thinking, oh yeah, I kind of see how this is working, you're right. And then E is just that n is even. Right? What's even mean? Well, the definition of even is you can represent it as n equals 2k for some integer. Right? That's the definition of even. Not for some odd integer, just for any integer. So we want to show that the set X is equal to the set E intersected with the complement of F. Right? So in the Venn diagram, the things that are not in F but are in E, right? Because it's we're intersecting with the complement of F. That's going to be the same thing as X. That will show that the two sets are equal. So we have to first show one that X is a subset of the intersection of E and the complement of F. We also have to show that E and the complement of F are a subset of X. One proof going in one direction, one proof going the other direction, and then we can show that they're equal. So let's start with the first one. Let's show that X is a subset of E intersect the complement of F. So if we assume that X is an element of X, right, we can say that X equals 2k for some odd integer k. We are assuming this to be true, right? That's how you generally do these proofs. And so X is even, right, because it can be written in the form of 2k. So therefore, we know that X is already an element of E, right? It's even. Now, what we want to do is suppose to the contrary that x is an element of f, as opposed to being in the complement of f. So if x is an element of f, then, and this is sort of proven by negation or whatever, x equals 4j, just using a new number so it doesn't get confused with our original k, 4j for some integer j. This implies that 2k equals 4j, or k equals 2j. But if k is 2j, then that 2j has to be even. Any number multiplied by 2 is even, right? That's the definition of even. So that contradicts the fact that k is odd, and therefore we know that x is in the complement of f, not in f. And so since x is an element of E and x is an element of the complement of f, we've shown that x is an element of the intersection of E and the complement of f. One implication down. If an element is in x, we know that it is in the intersection of E and the complement of f. Let's go the other direction. If an element is in E complement, or the intersection of E and the complement of f, does that imply that you're a member of x? So we can assume the first, that x is in that intersection. So then x is an element of E, and x is an element of the complement of f. So since E is an element of x, we can say that x equals 2k for some integer k, definition of even, right? So suppose to the contrary that k is even, right? Because remember, for it to be in f, right? For it to be in x, right? Then it has to be for an odd integer. And we've assumed that that we're trying to prove that it would be in x. So then if we assume that k is even and not odd, then k would be 2m for some integer m, because it's even, right? So we can define anything even as 2m. So that means that x would equal 2 times 2m, which is 4m. But 4m is the exact same thing as 4k, right? It's divisible by 4. So that contradicts the idea that x would be in the complement of f. Since we've assumed that, we have to say that k must be odd. Because if k were even, it would end up being in the complement of f, or not in the complement of f. And so that establishes that x is indeed an element of the set x. So since we've shown the implication going one way, and we've shown the implication going the other way, we can conclude that x and the complement, or the intersection of E and the complement of f, are the exact same set. QED is just a fancy word for it is proven in Latin, right? We're done. But there you go. The idea of having these ideas of sets, being able to define things mathematically and show the relationships between them, kind of important if we're going to talk about sets and groupings of people or objects or ideas or numbers or whatever. It's a way for us to express this stuff. Now we're going to throw out a couple more ideas. And again, we're going to use a lot of what we learned about with sort of predicate logic. There are going to be equivalents here in set theory. And you can kind of use them back and forth, the ideas. A couple other things, or a couple other ideas that are going to be helpful as we sort of try to define things mathematically. One, Cartesian products. So Cartesian products you kind of already have an idea for. If you have two sets, A and B, their Cartesian product would be the set of all ordered pairs that could be, connected between the two, where the first thing in the ordered pair is from the first set, and the second thing is from the second set, right? So the Cartesian of A and B is any A and B such that A is an element of the set A and B is an element of the set B. You kind of know this because Cartesian products are where we get Cartesian coordinates in like high school geometry, right? So we could say that the point AB is equal to the point CD if and only if A is equal to C and B is equal to D. You know that, right? Like 2, 3 is equal to the point in geometry 2, 3, and that's it, right? 2, 3 is not equal to 3, 2. 2, 3 is not equal to 3, 0 or 0, 3, right? It can't, 2, 3 is not equal to 1, 4, right? Where the sums would be the same. like you know that for it to work, like the first element has a meaning, right? It's your position on the horizontal axis. The second one has a meaning, it's position on the vertical axis. And so like you have to get the positioning and the numbers correct for them to be equal. And that's a Cartesian product. When you think of Cartesian products, think of the Cartesian coordinate system, and know that you can also have more than just two pairs. Well, for Cartesian, I think it's two, but like you could theoretically do a Z as well, whatever. And then the power set, sort of the last thing we'll talk about. So the power set is, it is the set containing all of the subsets that are possible when looking at a set. Let's talk about it in sort of real world terms. I think that'll be easier to understand. So if our set S is the set of all of the main characters from the sitcom Friends, right? Monica, Rachel, Phoebe, Ross, Chandler, Joey, right? The power set of that set would be all the different permutations of people who could go to the coffee shop that day, right? Central Perk, right? Yeah, I've seen enough episodes. I know what I'm talking about, right? So how many people? So what are all the possible combinations of people who go to the coffee shop today? Well, A, we know that the empty set is always a subset. So the empty set is in the power set. Nobody could go to the coffee shop today. Seems unlikely given the nature of the story, but whatever. Maybe it was their special London episode or whatever. So nobody could go to the coffee shop, right? Joey could go alone. Monica could go alone. Ross could go alone. Rachel could go alone, right? These are sets of single elements where one person goes alone. There'd be 6 of those, right? Then you'd have every possible combination. Well, Ross and Joey could go. Ross and Chandler could go. Ross and Monica could go. Ross and Rachel could go. Ross and Phoebe could go, right? Monica and all the different possible permutations of pairs of people going. That would be all your 2's subsets. Then, 3 people. It's every single possible permutation until you get to the final one, which is just all 6 friends go together, right? One subset of 6, which happens to be equal to the original set. So there you go. If S is all of the main characters in the sitcom Friends, the power set is all the different permutations of possible combinations of people going to the coffee shop today. There you go. As analogies go, it's probably not my best, but hopefully it makes sense for understanding the power set. Regardless, that's just a quick introduction into some ideas from set theory. We'll talk about it more as time goes on. And obviously, if you have any questions, feel free to send me a message in Canvas. Have a great week.